Hello, this is Jeffrey Fox. We're returning to our big data course where remember we're using clouds, we're running data analytics collaboratively, processing big data and solving problems in X informatics. This lesson discusses clustering with some examples, and we will actually come back to clustering later on in the course and present some Python code to implement it. Here, of course, are the usual array of X informatics fields that we're trying to address. This page here tells you some of the resources this lesson will use. There is a web link to a paper on clustering, which does not discuss the material here, but rather advanced clustering methods, which we will actually use in some of our work. But most of our discussion will be in terms of the Kmeans algorithm, which actually quite often gives very similar answers to the advanced methods. This particular lesson has no code. I say the code will come later, but we will use the plotviz program that we introduced a few lessons ago. We will also actually look at Wikipedia for their remarks on K-means and heuristics, and there will be some files which we will look at in the particular four files. There will be one called cluster-final-m3-c3 dating.reclustered. That is a plotviz file looking at the clustering of the dating data we got. Remember the 1,000 points describing the characteristics of possible dates. And then we cluster that into three clusters there. And just to show the difference, we have another file clustering it into 28. That's M30-C28. And we also have not one actually clustered algorithmically, but the actual input data from Harrington's book, which is the 1,000 points with the labeling of Harrington, and that's put in a form which allows us to display it in plotviz. Finally, there is a plotviz file of genomic data, which we will use towards the end to illustrate features of other applications that use clustering. So, what do you do to implement K-means? Well, we'll see it in real life if we know Python in a few lectures. But intuitively, or roughly, this is what happens. You choose the value of k. That is a weakness of this method. You really need to choose k in all the simple versions of K-means. The advanced version I mentioned, you do not choose k. You can choose a maximum value of k, but you can also choose other criteria, such as resolution, for specifying the number of clusters. Then you have an important step. You have to initialize the cluster centers, and this requires that the points live in a vector space. K-means, in fact, only works for vector spaces. We'll come across examples later on, like genomics, where there are no vector spaces. Anyway, you choose the centers of these clusters. And this means that K-means is not actually deterministic. Depending on the choice you make, you're actually going to get different answers. Often you just choose just one initial point. The Python code we'll look at later actually defaults to taking 20 separate choices for the centers, running K-means 20 times and returning the answer that gives the best clustering, where the best clustering is measured by how small the mean distances between points and their associated centers. Then given cluster centers, we go through an iteration. We take all the points and we take all the centers and assign each point to the cluster whose center is nearest to the point. And then we have an assignment of points to clusters, and we just calculate the center of the cluster as the centroid, namely the average in each component of the points assigned to it. So that's a very natural thing to do. And now we have a new set of centers. We have the same points we had before, and we just keep on iterating this process of assigning points to centers, calculating new centers, and then we do this until some criteria for stopping is met. You can look at whether the center positions change is small so that you don't think anything much will happen by continuing. You can look at changes in the distance between points and centers. Lots of possible stopping criteria, but I don't think that's algorithmically terribly important. And K-means is used very, very broadly. It's very simple and very fast. And there are many methods which are probably better than K-means, but they're often not used as much. An important thing which we'll come back to later on, and actually in a few lessons later on we'll give some more explicit examples, is that K-means can get the wrong answer. It's a well-known feature of this type of optimization problem that you can have so-called local minima, and we will discuss that briefly in this lesson. So here's a simple example I just took from Wikipedia. We have 11 gray squares. Those are the points, and we want to divide into 3 clusters, and we choose 3 cluster centers, inverted commas, randomly, and those are the red, the green, and the blue circles. Then we do the first step in the Kmeans algorithm. We associate points with centers. If you look at it, you can see that you will find 5 blue points associated with the blue circle, 5 green points associated with the green circle, and just 1 red point associated with the red circle. Actually, when you do K-means for real, you have to worry about clusters having no members, because if they have no members, you can't calculate their centroid, and special steps are needed for that particular circumstance. So now we've got a new association of points with centers, well, actually our first one, and now we can calculate the centroid of each cluster. The one case that's obvious is the red cluster. The centroid of the red cluster is that top red point, because there's only 1 point in the cluster. And then this is then shown in the next slide, 1 mark 3, the one on the left, and you can see that the red circle has moved to that red point. The green circle has moved a little to be nearer the centroid of those 5 points assigned to it, and the blue centers also moved a little. And then they finally iterate it and get an answer, and they actually even unfortunately displayed the answer incorrectly in Wikipedia. I looked recently, it's still incorrect, and they give these blue, green, and red circles as the centers, and they're obviously not the centers, so there's just a mistake in the picture. I have put the correct centers, which are the stars. So I think the points are correctly clustered, and we have correctly 3 clusters, 1 with 3, 1 with 4, and 1 with 5 points, and the red, green, and blue stars are the correct centers, and the blue circle might be the correct center, and the green and red circles are definitely the wrong center. So obviously what they did is they forgot to move the centers when they redid this.